Hi, this is the Science Chef. It's nice to be with you again. In this video, we'll be learning about the first part of a new series on an interesting and important topic in chemistry, which we title Introduction to Mole Concepts. So go nowhere, I will be right back after this timeout. Welcome back. The mole is defined as the amount of a substance that contains as many elementary entities as there are present in 12 grams of carbon-12. These elementary entities can either be atoms, molecules, ions, or electrons. 12 grams of carbon-12 is used as a reference because it is the most stable isotope of carbon. A mole is used by chemists to bring different measurable parameters of substances to the same unit for easy comparison. These parameters include the mass, volume, number of particles, and concentration. Let's now look at the relationship between the mole and these parameters. In terms of mass, the mole is considered to be the molar mass, which is the mass of 1 mole of a substance expressed in grams. It is calculated by finding the algebraic sum of the relative atomic masses of all the elements in the substance. If the substance is a compound or polyatomic molecule, then the molar mass is equivalent to its relative molecular mass. However, if the substance is just an atom of an element or a monatomic molecule, then its molar mass is equivalent to its relative atomic mass. In terms of volume, the mole is considered to be the molar volume, which is the volume occupied by 1 mole of any gas at standard temperature and pressure. It is a constant and has a value of 22.4 dm³. In terms of number of particles, the mole is considered to be equivalent to the Avogadro's number, which has a value of 6.02 times 10 raised to the power 23. This means the amount of any substance that contains this number of particles equals to its mole. Therefore, you can redefine the mole as the amount of any substance that contains the Avogadro's number of particles. Just liken the mole to a dozen, which represents 12, with half dozen representing 6 and 2 dozen equivalent to 24. In terms of concentration of solution, it is considered to be the molar solution, which is the concentration formed when 1 mole of a substance is dissolved in 1 dm³ of water. In chemistry, we deal with amounts of substances which may not necessarily be equal to their molar values, hence the need to know how to convert them to mole. To convert mass to mole, we use the formula mass in grams over molar mass in grams per mole. And to convert volume to mole, we use the formula volume in dm³ over molar volume in dm³. Similarly, to convert number of particles to mole, we use the formula number of particles divided by Avogadro's number. And finally, to convert concentration of a solution to mole, we use the formula concentration in moles per dm³ by volume in dm³. It's now time to look at some examples on mole conversions. Example 1. Calculate the number of moles present in the following substances displayed on the screen. In example 1a, b, and c, we are expected to convert grams to number of moles. So what we'll do first is calculate the molar masses of the given substances, one being the molar mass of chlorine, and that one the molar mass of sodium triiodocarbonate 4, that's Na2CO3, and the last one the molar mass of oxygen atom. So let's start with the molar mass of chlorine. Example 1. So 1a, chlorine is a diatomic molecule, so its molar mass will be 2 times the relative atomic mass of chlorine. And the relative atomic mass of chlorine as given in the question is 35.5. This will be 2 times 35.5, and that gives us 71 grams per mole. 31 grams per mole. So 1 mole of chlorine weighs 71 grams. So X mole of chlorine will weigh 7.1 grams. right? So solve for x. Similarly, you can use number of moles of chlorine equal to mass of chlorine over molar mass of chlorine. So the mass of chlorine here is 7.1 grams divided by 71 grams per mole, and that will give us 0.1 mole of chlorine. 1b, calculate the molar mass of Ne2CO3 2 times the relative atomic mass of sodium plus 1 times the relative atomic mass of carbon plus 3 times the relative atomic mass of oxygen. The relative atomic mass of sodium, as given in the question, is 23. 2 times 23 plus 1 times relative atomic mass of carbon, as given in the question, is 12. And relative atomic mass of oxygen, as given in the question, is 16. So if we evaluate this, we get 106 grams per mole. Similarly, we can use number of moles of Na2CO3 equals to mass of Na2CO3 divided by molar mass of Na2CO3, and that will give us 1.06 grams divided by 106 grams per mole, and this gives us 0.01 mole of Na2CO3. So to use any method that's convenient for you. 1c, to calculate the number of moles present in 3.2 grams of oxygen atom. Here we are given oxygen atom. Oxygen atom is just O, and the molar mass of oxygen atom here will be equal to the relative atomic mass of oxygen, which is 16. Remember, oxygen is a diatomic molecule, O2, but here we are given an oxygen atom, which is only one atom of oxygen. So the molar mass of this atom of oxygen will be equal to its relative atomic mass, which is 16. Similarly, we can use number of moles of oxygen atom equals to what? Mass of oxygen atom divided by what? Molar mass of oxygen atom, which will be 3.2 grams over 16 grams per mole of oxygen atom. So that will give us 0.2 mole of oxygen atom. In example 1D, convert number of atoms to number of moles and vice versa. The atomicity of the substance must be taken into consideration. When converting the number of moles to number of atoms, we multiply the number of moles by the Avogadro's number and the atomicity of the substance. However, when converting from the number of atoms of a substance to number of moles, we divide it by the Avogadro's number and its atomicity. This only applies to number of atoms and not number of molecules, nor number of ions. So to calculate the number of moles present in 6.02 times 10 to the power 23 atoms of oxygen gas, we'll divide that value by the Avogadro's number and by 2, since oxygen is a diatomic molecule, like this. F, we have to convert Similarly, we can use number of moles of chloride ions to be equal to what? Number of particles. Number of particles of chloride ions all over Avogadro's number. Avogadro's number of chloride ions, which will give us F, to convert 11,200 cm cube of carbon dioxide gas to mole at STP. Okay, so 1 mole of carbon dioxide will occupy what? 22.4 dm cube at STP, right? Or which is equivalent to what? 22,400 cm cube at STP, since 1,000 cm cube 1,000 cm cube equals to 1 dm cube. Okay, so X amount of carbon dioxide will occupy 11,200 cm cube at STP. Similarly, if we use number of moles of CO2 to be equal to volume of CO2 over molar volume at STP. This will be equal to 11,200 cm cube divided by 22,400 cm cube per mole at STP. So that gives us 0.5 mole of CO2. And lastly, G, we are asked to convert by the number of moles present in 250 cm cube of 0.1 molar H2SO4, 0.1 molar H2SO4 solution. So this one just goes straight to the formula. Number of moles of H2SO4 will be equal to what? Concentration of H2SO4 times volume of H2SO4 in dm cube. What's the concentration? Given concentration is 0.1 moles per dm cube. 0.1 moles per dm cube times the volume. The volume must be converted to dm cube. So it'll be 250 over what? 1000 dm what? Cube. Okay. If we evaluate this, we obtain 0.025 mole of H2SO4. Example 2. Calculate the volume of substances present in the following at STP as shown on the screen. In example 2, the questions can be approached from different ways. We can either convert the given values to number of moles and then convert the number of moles to volumes at STP, or we can simply equate the appropriate mole formulae and solve for the volumes at STP as shown. Since this is mass, since we are given the mass of SO2 here, then we have to determine the molar mass of SO2. Molar mass of SO2 is 1 times AR, relative atomic mass of sulfur, plus 2 times the relative atomic mass of oxygen. And this gives us 1 times 32 plus 2 times 16. That's 32 plus 32. That gives us 64 grams per mole. You can easily say 1 mole of SO2 occupies 22.4 dm cube at STP, which means that 64 grams of SO2 will occupy 22.4 dm cube at STP. Therefore, 16 grams of SO2 will occupy X. Similarly, if we use mass of SO2 over molar mass of SO2 equals to volume of SO2 over molar volume. I will make volume subject of volume of SO2 subject of formula. This will be mass of SO2 times molar volume all over molar mass of SO2. So this gives us B. We are told to convert one mole of ammonia gas occupies 22.4 dm cube at STP. How many molecules are present in 1 mole of ammonia gas? 6.02 times 10 raised to power 23 molecules of ammonia gas will occupy 22.4 dm cube at STP. Therefore, 3.01 times 10 raised to power 22 molecules of ammonia gas will be present in what volume of ammonia at STP. So we solve for X. Alternatively, we can use number of particles of ammonia divided by Avogadro's number equals to volume of ammonia all over molar volume. So we make V here, volume of ammonia, subject of formula. That will be what? Number of particles of ammonia times molar volume of ammonia divided by Avogadro's number of particles. What's the number of particles? What's the number of particles given in the question? That's 3.01 times 2C. 2C, you're asked to convert this is number of atoms, so we must take the atomicity of sulfur 6 oxide into consideration. So for a molecule of sulfur 6 oxide here, or a mole of sulfur 6 oxide, that's SO3, contains 4 atoms. As we can see here, 1 atom of sulfur and 3 atoms of oxygen. So, which means that the atomicity of sulfur 6 oxide here is 4. So we have to take that into consideration. So it means that 1 mole of sulfur 6 oxide will occupy 22.4 dm cube at STP. Right? Now, what is the number of atoms present in 1 mole of sulfur 6 oxide? There will be what? 4 times 6.02 times 10 raised to power what? 23 atoms. of sulfur 6 oxide will occupy 22.4 dm cube at STP. Remember what we explained in example 1. How much volume will 1.505 times 10 raised to the power 23 atoms of SO3, sulfur 6 oxide, occupy? If we solve for that, so it's now your turn. We'll post the solution to this task 24 hours after publishing this video on our community tab. In our next tutorial, we'll be looking at the second part of this series on mole concept, the application of mole concept. If you would like to be notified when the video is published, subscribe to our channel and turn on the notification bell. Remember, winners don't quit and quitters never win. Keep winning and stay safe till I see you when I'll see you.